we start to talk about how we identify the boundary layer thickness. And these are two other definitions that, for the sake of time, we're going to ignore. So the boundary layer thickness is the vertical extent of the shaded region. Well, clearly, if we're looking at a fluid in a flume or something like that, one part is not shaded and one part is unshaded, right? So we have to make that distinction ourselves. And so this boundary layer thickness here, we define as the vertical distance from which the velocity goes to zero, or from zero, up to 99% of the free stream speed, right? Or basically approximately recovers to the free stream speed. Okay? So the vertical distance over which this happens is the boundary layer thickness. Okay? And so we can say that the boundary layer thickness is the y-coordinate at which the local velocity recovers to 99% of the free stream velocity. And again, we're going to sort of skip over this stuff, and we're going to come to here. All right. So just to sort of reorient where we are and where we're headed, we're looking at flat plates to differentiate between the pressure drag and the viscous drag, right? The forces associated with pressure versus the forces associated with viscosity. We are differentiating them to only focus on viscosity by using an infinitely thin flat plate. If we knew the velocity profile at each point along the plate, we could calculate the shear strain rate. We could multiply that by the absolute viscosity and get the local shear stress. We could multiply that by the area and get the viscous force. So as you might be surprised, we're going to come back here to the simplified Navier-Stokes equations and the continuity equation. We've already assumed two-dimensional, right? All of the W and Z terms are gone. We've assumed that it's incompressible. And so we've got this continuity equation here, and we've done away with body forces. We assume that they're fairly small in comparison to potentially the pressure forces and the viscous forces. Figure 9.9 is an important one to consider. If we look at this top plot here, again, here is the leading edge of the plate, and we have the coordinate in the x direction. In the vertical axis here, we have the boundary layer thickness. And you can see that the boundary layer thickness increases with x. It increases with the distance from the leading edge. And at some point, we have the critical Reynolds number. And the critical Reynolds number that we're going to use for this class is 5 times 10 to the 5th. So it's the length at which the Reynolds number becomes 5 times 10 to the 5th, and thus goes from being laminar to turbulent, as you can see differentiated here. Again, on this bottom plot, we go from the leading edge, and we increase in x as we go. And this is the wall shear stress, where you can see that as the boundary layer thickness increases, the shear stress actually decreases for laminar flow until we get to the point where it trips to turbulence, and then it hops up and does something different. So it would be very beneficial to know what the velocity profile was at any point along the plate. And the next couple of pages talk about how we do that for laminar flow only. This is referred to as the Blasius solution, and it's not overly complicated, but I'm not going to spend a great deal of time on it, and if you're interested, you can certainly read here. It's very well explained. But essentially, what we're going to do here is we assume that the velocity in the vertical direction is very small with respect to the velocity in the direction moving along the plate, and that we assume that changes in x are fairly small compared to changes in y, right? And we've made both of these assumptions many times before in this class. We also are going to assume that the pressure forces in this case are unimportant. And what this equation right here says is that the shear stress is balanced by the momentum. Okay? So we're also going to set boundary conditions here, that at the plate the velocity is 0, And as y continues to increase, the local velocity goes to the stream, the free stream velocity. And then over here, we're going to do a little razzle-dazzle with some terms to non-dimensionalize. You've seen u over u before, and we're going to non-dimensionalize the boundary layer height, and they're going to introduce the similarity variable and the stream function. This is all an effort to reduce the number of variables so that we have fewer unknowns so that we can consider this problem well posed. After having done all that, we come down to this third order nonlinear differential equation. And as you know, we can't actually solve this exactly, but we can approximate it, as you probably did in differential equations class, by a series of linear differential equations. And in so doing, we come all the way down here to one of the more important equations in fluid mechanics, or expressions, I guess, and this is equation 915. This is the boundary layer thickness is equal to 5 times the square root of the kinematic viscosity times the distance to the current point from the leading edge divided by the free stream velocity. Now, you might be wondering where we get this 5, so hold on to that for just a second. If we look at figure 9.10, in A, we have essentially the non-dimensional velocity. So here's 0, and here we come back to the free stream velocity, 1.0. So this is 100% you can think of the free stream velocity. And in this case, we have the similarity variable, but we can really think about this as the non-dimensional height above the flat plate. And you can see here that the velocity profile recovers to 99% of the free stream velocity at 5 non-dimensional heights, right? So that's where this 5 comes from here, or this 5 comes from in equation 915. Okay? Now in B here, what we show, this is a very interesting result. So this first line here is where x is equal to x1, and x1 is just some value. You know, we call it some distance from the leading edge. If we multiply that by 4, which is to say we go 4 times that distance down the plate, we get this profile. If we go 9 times down that distance, we get this one, 16 and 25, etc. And so this is the velocity profile. And what you can see is that essentially the du dy, right, the shear strain rate, is decreasing with increasing distance down the plate, right? Each of these curves represents a new and further distance down the flat plate, okay? So if du dy is decreasing, then the shear stress is also decreasing. And we can look back at this qualitative plot here, and we get the same idea here, right? That the shear stress is decreasing for laminar flow in the direction of flow. And the reason that is because you can see this distance here at which the velocity recovers to the free stream velocity, right? The distance at which the local velocity is 99% of the free stream. Well, this distance, which is the boundary layer thickness, by the way, is increasing. And so essentially what we're doing is taking the velocity profile and stretching it over a greater and greater vertical distance. And as we stretch it, we decrease du dy, and thus we decrease the shear stress. Pretty slick, huh? Now, the last thing that I'd like to talk to you about here is how we calculate the wall shear stress. And we come up with that from this simple expression here. This is equation 918, which you'll find useful. And we've got 0.332 times u to the 3/2 times the square root of the density of the fluid times the absolute viscosity of the fluid divided by the distance from the leading edge. And you might be surprised to learn that at a given x distance, the slope of this line right here turns out to be 0.332, which is where that number comes from. So that's where we're going to stop. I'd just like to recap very quickly. So the idea is that we are looking for the lift and drag. Ideally, that's what we want to know from all of these shenanigans. If we knew the pressure profile and we knew the velocity profile at each point, we could then decompose them into forces in line with the incoming velocity, which we'd call drag, and those orthogonal to the incoming flow direction, which we'd call lift. But unfortunately, we can't do that. So we've come up with an empirical correlation instead, which changes based on geometry and Reynolds number and a bunch of other stuff, which we'll get to. But these ones work pretty well. They're just fairly limited. But what we'd like to do is maybe come up with something that is a little more powerful and a little more wide-ranging. And so what we're going to do is we're going to start considering only the viscous forces, and then we'll consider the pressure forces separately. So in order to consider the viscous forces, we think of an infinitely thin flat plate so that we remove all consideration of the pressure forces and only consider the viscous forces. We have a region out here that is the boundary layer, where the viscous effects are unimportant, and a region inside where the viscous effects are important. And we have a vertical distance above the flat plate at which we draw that boundary line. That is the boundary layer thickness, and the boundary layer thickness is defined as the point, the vertical point above the plate at which the velocity recovers to 99% of the incoming flow velocity. So ideally what we'd want to be able to do is determine the boundary layer thickness and the velocity profile at each point. And through the Blasius solution, we can do that. We can figure out what the velocity profile is, and from that, what we really want to know is the shear stress at each point. This applies only for laminar flow, but it is incredibly powerful because this means we don't have to conduct experiments. We have basically the correlation that gives us the answer at any x point. We can figure out what the wall shear stress is. If we can sum all those up, we can figure out what the viscous force is on a flat plate of some given dimension.